All right, so let me give you that sort of idea for the rest of the kind of deal here. So we have this thing that we call Green's theorem, right? What does Green's theorem do?
How much a field helps you along the path.
Yeah. So Green's theorem takes a closed integral around a loop, right, of some vector field dotted with dr, and gives you an alternate way to express this in terms of what? So it takes a line integral and turns it into a an area integral, right? Maybe. Really, honestly, this is a double integral sign that I'm thinking, right? So this is the integral dA of what, like the partial of q with respect to x minus the partial of t with respect to y. And really, in some sense, right, this thing really reads, this is the circulation right, is total curl. That kind of makes sense? That's Green's theorem. The next one, the one that we are going to talk about today, which I guess I can introduce now, is this thing about the divergence theorem. Okay, and the divergence theorem, hi Henry, says that when you have a integral over a surface of a vector field dotted with the area, what's my interpretation for this thing? Yeah, this is the kind of net flux, right, through the surface S given by this vector field. So that's, right, earlier we were talking about tornadoes. This is sort of, if I put a screen door out in the world, and I think about the vector field of the wind blowing around, that's going to tell me how much wind is passing through through that screen door. You see that thought?
Per unit time, right?
Yeah, per time unit. So that's what this guy would be, right? This is the flux. So if I close that surface S, right? If I have a closed surface S, I could say that this stuff, right, my flux integral, is the sum of the divergence of F with respect to volume. So this is total divergence. Total divergence. And we don't really have an idea of what divergence is right now. But if you just assume that's kind of the net creation or contraction of air, that would sort of make sense, right? If I have a closed surface, like a big spherical net, and I'm asking about the flux through that thing, well, if it's closed, right, either there's air going into it and it's collecting there, or there's air coming out of it, right? So that's really what this guy is. This is just telling you, if you go look around in the sphere, how much more air or less air are you getting?
If it was just like wind going in one direction, it'd be zero.
Yeah, so if it was going through one side, or in through one side, out through the other, yeah, the total would be zero. You guys see that? So that's really what all three of these things, Green's theorem, the divergence theorem, and there's this other thing, Stokes. And Stokes' theorem really says that the integral around a curve C of F dotted with dr is really just kind of this thing amped up. So this is the integral of the curl of F dotted with the area over the surface S. The idea here being, if I had some kind of funky two-dimensional shape that I wanted to, some handkerchief, right, like a surface, and I want to apply Green's theorem to this, I can't because it doesn't live in 2 dimensions. But let me just amp this up. And it says the exact same thing, right? The circulation around the edge is the total of the curls on the surface.
So in Green's theorem, C represents a path.
Yeah, so C's a path here. Oh, and I missed a D for a domain. So in this picture, right, I've got a path around some region D. So C's this kind of looping around the outside, D's a region. If I kind of puff D up into a 3-dimensional object, the thing that Green's theorem says is still sort of true. You just have to be a little more careful with it. Okay. I'm glossing a ton of orientation stuff and signage and assumptions, but this is kind of the idea, right? So Green's is circulation is the total curl, divergence is the total, right? The flux is the total divergence, and then Stokes is going to read what? If I wanted to write an equivalent blue sentence for Stokes, what would it read?
Circulation around the outside is the curl.
Yeah, it really would read the exact same thing as Green's, right? It's circulation is total curl.
And when you say circulation and curl, you're thinking of something like a wave pool or a whirlpool?
Yeah, so I'm thinking of adding up the local tendencies to whirlpool. And that gets a little bit more complicated in 3 dimensions. We haven't talked about what 3-dimensional curl means yet, but it's all
more like
there.
tornado almost.
Yeah, it's
Cyclone.
right, but cyclones have a, cyclones on the Earth always point up,
Yeah.
right? They don't really have to point up in terms of airflow, right? You could certainly have a sideways cyclone.
Yeah.
So I need some circulation and a direction around which it's happening. Cool? This kind of help. Like the idea is really, I want to take a line integral or a surface integral and turn it into something a little different at least, in hopes that it might be more convenient. Cool?